Hi, this is Yixuan from The Ohio State University. Today, I'm going to present our work on NeuralKalman, a learnable Kalman filter for acoustic echo cancellation. This is a joint work with Meng Yu, Hao Zhang, Dong Yu, and Deliang Wang. Acoustic echo cancellation is widely used in mobile communications and teleconferencing systems. It aims at removing echo from microphone signal. The right figure shows an acoustic echo scenario with background noise, where the far end signal goes through the speaker and reaches the microphone in the near end as echoes. The microphone signal from the near end comprises of echo D of T, near end speech S of T, as well as potential noise N of T. The AEC system uses far end signal X of T as reference, eliminates the echo from microphone signal Y of T, and send the estimated near end speech to the far end speaker. There are many conventional signal processing algorithms, such as NLMS, and also DNN-based methods that treat AEC as a source separation problem have been studied for AEC. And in recent years, hybrid methods that combine both, such as deep adaptive AEC that is based on an NLMS algorithm, where a linear algorithm is embedded as differentiable layers, has been found highly effective in modeling time-varying echo paths. And frequency domain Kalman filter, abbreviated as FDKF, compared to other linear adaptive algorithms, shows robustness in double talk scenarios and better convergence rates, and has not been well studied for hybrid methods. In this work, our goal is to develop a hybrid model based on FDKF that maximizes the benefits of both FDKF and DNNs. This figure shows a diagram of a frequency domain Kalman filter, where Y is the microphone signal, X is the far end signal, and W hat K represents the estimated echo path, and S hat represent the near end speech signal. It consists of a prediction step and an update step. In the prediction step, the estimated echo path is applied to the far end signal to get the estimated echo. The estimated near end speech is obtained by removing the echo from the microphone signal. In the update step, the estimated echo path is updated based on the estimated echo path from the last frame, Kalman gain, as well as estimated near end speech from the last frame. A here represents the transition coefficient, which is often tuned manually. And K of K represents Kalman gain, which is updated using the last two equations. In these equations, the covariance matrices psi VV and psi delta delta are approximated using estimated near end speech signal and estimated echo path. And there are some weaknesses of the frequency domain Kalman filter, as you might notice from the definition. First, the loudspeaker nonlinearity is not considered in the far end signal. And second, in the echo path estimation, the covariance matrices are approximated, introducing errors. And finally, the transition coefficient A is manually tuned, which needs to be tuned to fit different data. In this study, we propose NeuralKalman for AEC. The right figure shows the overall structure of NeuralKalman. We use DNNs to estimate the transition factor, far end nonlinear distortion, and the nonlinear transition function in the frequency domain Kalman filter. The input feature is first computed from the complex STFT of the microphone and far end signal. which is a concatenation of temporal correlation, frequency correlation, channel covariance, and normalized log power spectrum of microphone and foreign signal. The input feature is then sent to an RNN, which is followed by two branches for estimating nonlinearly distorted foreign signal and transition factor. The shared RNN is a 4-layer long short-term memory network where each layer has 257 hidden units. This slide shows the details of the module for nonlinear distortion estimation. The right figure highlights the modules for estimating nonlinear distortion. And in this subnetwork, it is responsible for estimating the nonlinear distortion consists of a linear layer with rectified linear units activation, followed by two one-dimensional convolutional layers. And the nonlinearly distorted foreign signal is obtained by applying the complex valued ratio filters to the microphone signal. And after that, the estimated nonlinear foreign signal is used as a reference for updating Kalman filter. Here we talk about the modeling of nonlinear transition function. And as we discussed in earlier slides, in the estimation of echo paths, the covariance matrices are approximated, introducing errors. And we find that incorporating direct covariance modeling enhances the performance. However, through more experiments, we find that introducing a nonlinear transition function in the state equation leads to a comparable performance improvement with less computation. And the subnetwork is shown in the right figure. It consists of an LSTM cell with 256 hidden units and two linear layers for estimating real and imaginary parts of the output. This slide discusses the modeling of transition coefficient A. The transition factor A in the range of 0, 1, and 1 depicts the variations of Kalman filter, and it is often manually tuned to a value that is close to 1. And in NeuralKalman, we employ DNN to estimate a time-varying transition factor. And the DNN module for estimating a frame-based transition factor takes RNN's output as input and is composed of a linear layer followed by a sigmoidal activation function. For the experimental setup, we simulate the dataset using AI Shell 2 and AEC challenge datasets. More specifically, we use clean and nonlinear distorted foreign signals from AEC challenges synthetic echo set. And the nonlinear distortions such as maximum amplitude clipping with a sigmoidal function, learned distortion functions, etc. are included. And we generate 10,000 RIRs using the image source method with RT60 from 0 to 0.6 seconds. And we randomly pick signal to echo ratio from -10 dB to 10 dB in the generation of the datasets. In total, we generate 90,000 utterances for training, 200 for validation, and 300 for testing. And the test set is generated from utterances and RIRs that are not seen in training process. During training, we train our models for 90 epochs, and we randomly selected 10,000 utterances in each epoch. The loss function we choose consists of SISDR loss as well as frequency domain MAE loss. And we evaluate our models using PESQ, PESQ, and word error rate. And for the input feature, as shown in the right figure, it takes the complex SDFT of the microphone and foreign signals as input, and the concatenation of normalized log power spectra of microphone and foreign reference, as well as three features, including temporal, frequency correlation, and channel covariances, are sent to the linear projection layer, whose output serves as the input feature for the following RNN network. To evaluate the effect of modeling each component, we conduct an ablation study to test the performance of NeuralKalman with various settings. For nonlinear distortion modeling, while the influence of modeling G has been discovered in the second paper in the reference, we also observe that the key improvement comes from modeling the far-end nonlinear distortion. We find that by solely estimating A, we achieve a PSQ score of 2.32 and a word error rate of 31.67%, which is slightly better than the common filter. Compared to only estimating A, we find that further introducing far-end nonlinear distortion which corresponds to the NeuralKalman GA in Table 1, increases the PSQ by 0.25 and reduces word error rate relatively by 29.4%. We find that by learning the nonlinear transition function, the performance of NeuralKalman is further improved. For example, when we compare the NeuralKalman GA, the Pascal of NeuralKalman GTA is improved by 0.1, and the word error rate is relatively reduced by 8.8%. And we also test the NeuralKalman model, NeuralKalman G psi A, which where we substitute approximated covariance matrices in the frequency domain Kalman filter with DNN learned covariance, and has shown improved performance in terms of all metrics. However, we find that compared to directly estimate the covariances, the NeuralKalman GTA can achieve slightly better performance with less computational cost. In addition, we also trained a NeuralKalman network that estimates both the covariance and nonlinear transition function, where we find that estimating both does not bring further improvement. Finally, as shown in the right figure, we observe that estimating nonlinear transition function brings faster training convergence speed, and therefore we decide to only estimate the nonlinear transition function T instead of the covariance psi. As shown in the table, we validate the necessity of estimating A by eliminating the estimation of A from the best performing NeuralKalman GTA. And where we find that the PASC is reduced by nearly 0.1, and the word error rate increases to 21.98%. In addition, to examine the response of A in the scenario of abrupt echo path change, we have also evaluated a model that solely estimates A, where we name it as NeuralKalman A, on the sample with abrupt echo path change. And in the RIR is abruptly switched from one to another at the indicated position in the figure. And we plot the value of learned A from the NeuralKalman A model on audios with and without abrupt echo path change. It is observed that the audio signal without echo path change, the learned transition factor A is close to 1 and relatively stable throughout time, which explains why the performance of NeuralKalman A is similar to that of the frequency domain Kalman filter. And for the signal with abrupt echo path change, we observe that the value of learned A decreases to nearly 0 when the echo path abruptly changes and gradually increases afterwards, which is reasonable to obtain a stable convergence. We believe that it is proper to use a time-varying A in scenarios with echo path changes to make the updating of the algorithm stable and diminish the chances of divergence. Here we compare the proposed NeuralKalman GTA with strong baselines, including the frequency domain Kalman filter, NLMS-net, and DNN-AEC, where the NLMS-net is based on deep adaptive AEC and DNN-AEC is based entirely on DNNs that uses the microphone and foreign signal as input to directly predict the speech at the near end. And both of the NRMS-net and DNN-AEC adopt the same RNN network, input feature, and loss function as the proposed NeuralKalman, and both of them are trained using the same dataset as the proposed NeuralKalman. And from table 2, first we find that all hybrid methods outperform the frequency domain Kalman filter algorithm. And second, among the hybrid method, NeuralKalman has the best performance, and NRMS-net does not show superiority over DNN-AEC when trained on data with stationary echo paths. Compared to NRMS-net, the NeuralKalman improves the PASC by 0.15 and relatively improves the word error rate by 12.5%. And NeuralKalman outperforms the DNN-AEC in terms of PASC and word error rate, with PASC showing a 0.05 improvement and the word error rate showing a relative improvement of 11.8%. In summary, we find that NeuralKalman tackles Kalman filter's weakness, including not assuming nonlinear distortions in the far end, the parameter tuning need, as well as potential errors caused by approximations in the echo path estimation. Simply replacing more components in Kalman filter with DNN doesn't always bring better performance. In general, we observe that estimating missing or approximated components in Kalman filter could bring potential improvements. Also, a better designed adaptive algorithm can bring more potentials to the hybrid network. And in future work, we will explore training NeuralKalman on real recorded signals with echo path changes and utilizing it in real-world devices. We also provide a demo page showing the spectrograms of a microphone signal, target signal, as well as the outputs of the Kalman filter, NRMS-net, DNN-AEC, as well as our proposed NeuralKalman. From the spectrogram, we find that the frequency domain Kalman filter's ability to suppress echoes appears to be limited. And hybrid methods such as NRMS-net shows promising echo suppression results in double talk regions. However, the echoes remain present in the single talk regions. Here I'm going to play some demos. The first one is the microphone signal.
Was a homely enough figure. The routine of his life was simple too.
And this is the target signal. This one is the output of Kalman filter. I'm going to play it again. This one is the output of NLMS-net. This one is the output of DNN-AEC. And the last one is the proposed NeuralKalman. Among the baseline methods, DNN-AEC and NeuralKalman demonstrate better effectiveness in removing echoes. That's all for my presentation today. Thank you for listening.